Okay, so today we're going to have a look at the chemical industry. Basically, the chemical industry is when you've got some materials, raw materials or your feedstocks, and you're going to turn these into consumer products. So there's a kind of cycle there. It's all done kind of big companies on a big scale. But the main thing is that I kind of wanted to talk about is this word profit. Now, any kind of business would use these things to make money, and they'd be trying to make as much money as they possibly can, reducing as much waste as possible, and they are going to try and put the least amount of money into something as they have to get the most money. That's how a kind of business works. So that's what kind of profit means. So the basis of a chemical industry is to make a profit by changing raw materials into feedstocks and consumer products. So we're going to have a look at what these two words or these two terms mean: raw materials and feedstocks. And a consumer product is just like a kind of end product. So the chemical industry, you might have a chemical plant that makes hydrogen peroxide, which could be used in like bleaching your hair and your teeth whitening. So before any of that happens, before you make a new product, you've got to go through some cycles to actually work out how best to actually do the process to make it work well, reduce the amount of waste, and spend as little as possible to get the most money back. And there's a kind of cycle, there's a development cycle that they would go through. I'm just going to talk through the stages. So you start here, you start at the research stage, and then you just kind of work your way around. So the first step is doing research and development, and that's when you find out new structure properties and method of preparation. So they might start with a new chemical that they want to make, or they might have a chemical they've already made, but because they've already been around this cycle that we're going to talk about, they've maybe worked out a new way to make it that's more efficient, it's going to cost them less, and going to make them more money in the long run. The next stage is a kind of pilot study, and that is when you kind of scale up slightly, but not go into like a full industrial scale. You have kind of scaled it up, you're trying to work out kind of the process you would follow, and the best kind of way of making it, and that's what you would do in the pilot study. So it's a wee bit like research and development on a kind of slightly larger scale, just to make sure that you're getting the right process that you're following to get the best way to make the chemical. The next step is scaling up, and that is when you're going to make it into like a proper production plant. Okay, at this point you would work out the best conditions in your particular plant for the best yield, the best way of doing it. You might have temperatures that you carry out, pressures to get the best yield. Okay, so that's what happens when you scale it up. And then once you've scaled it up, you just keep the plant running, and that's the production. So basically that will just keep happening until maybe, I don't know, they might go 6 months, and they might start looking at it, analysing and seeing if there's any way that they can improve it. What's going well, what's not going well, is there anything they can change to make it more efficient? That would then be the review stage. And then at that review, they would change the production slightly. So this cycle's probably happening all the time in chemical plants around us, okay? So start with research and development, then we go to the pilot study, which is scaling up a wee bit, then you scale it up fully to the full production kind of amount to work out the best kind of conditions. Then you actually just keep it going at the plant, that's the production, that's when you actually make your stuff, and then after about 6 months you might have a review. Okay, so hopefully that makes sense. When they are designing a process, there's these 7 principles that they'll follow. We're going to come back to these, I'm going to kind of talk about them, and it should make sense when we do a kind of example. So availability of a feedstock, it's probably going to be helpful to tell you what a feedstock is, but just we'll come back to that. Basically, these are the chemicals that you're going to use to make your final consumer product. I'm going to go over a definition in the next couple of slides, but I'm just going to use these just kind of to give you an idea. So availability of it, is it quite easy to get? So for example, if you are doing something that involves making something from petrol to turn it into plastic, say you were doing something like that, then you would want to have a good supply of petrol. So if you are living in the middle of Antarctica, then that's not going to work very well, because you're not going to be able to get that kind of available quite easily. It would take a lot of effort to get that petrol to come to Antarctica. The cost of the feedstock, so if we're using petrol, then that's going to be quite cheap compared to something like if you were making something from gold, that's going to be very expensive, so that's going to be not very feasible to happen. So you'd obviously, petrol is quite cheap, so if you were using petrol in your kind of process, then that'd be quite nice, quite easy to use, quite cheap. Sustainability, again, if we were using gold, then most of the world's gold has already been mined because it's an unreactive metal. It's been in the earth for ages, so people have already dug out, so it's quite difficult to find new gold. Whereas petrol, we're still finding new petrol under the sea from the crude oil, so that's there quite a lot. We're still finding new oil beds, they're called, which is where you'd put the drill in and you kind of mine the oil out. So obviously petrol is going to be more sustainable than gold. Opportunities for recycling. If you maybe make a wee byproduct, can you put that back in your chemical process in any way to maybe reuse it to save you getting new stuff in? Recycling is obviously going to save you money in the long run. Energy requirements, so you might want to maybe think about using a catalyst to reduce the energy needed for your reaction to take place. That would save you some energy. Or maybe you might want to think about recycling energy that you find from an exothermic reaction. You could reuse some energy that's given out in an exothermic reaction. Any byproducts you might make, if you make something, then are you able to sell them off as well? If you can, then that's going to be a major waste. Whereas if you were, say, making plastic and it gave off hydrogen, then you could actually sell that hydrogen on in canisters, because hydrogen can be used as a fuel as well. So that's obviously going to be quite nice. Obviously, if we were giving off nitrogen gas, the air is made up of like 70% nitrogen, or sorry, 78% nitrogen. So that's not going to be all that helpful. And your product yield, obviously you want to try and make your yield as much as possible. You don't want to be wasting lots of stuff. Again, thinking about the money, you want to be trying to make as much of your product as you possibly can to get the most money back at the end. So we're going to talk about these definitions here. Okay, so we've talked about this, the processes and the sim principles of the design process, like what they follow. Here is what these definitions are. So raw materials are basically original substances as we find them from the earth in their raw form. So that might be fossil fuels such as coal, oil and gas. Metal ores, which are kind of rocks which have metals in them, but they're joined to other elements, so we need to basically break those down if we were to try and find a metal from that. Minerals, which are basically just salts, and you can find them as rocks. Air is a raw material. Sulfur, sea salt and water. Okay, so they're all raw materials that we could actually get from the earth without doing anything to them. They're in their raw form. So we need to know this definition. So I would put that in your jotter or something, make sure you know that. Also, these are going to be quite important as well, so you might want to have these in your jotter as well. And a feedstock is basically something that has, it's not its raw form, but your raw form, something that's in its raw form from the earth, has been maybe processed into this chemical that can be used for lots of different applications. That is what a feedstock is. So it can be a substance or a mixture of substances from which other chemicals can be extracted or synthesized. Synthesized is just a fancy name for being made. Okay, so if I was to synthesize sodium chloride, I would be reacting sodium with some chlorine gas to make some sodium chloride. Now, examples of these are ethene, synthesis gas, which is something we've not talked about at Hire, but we used to talk in the old Hire, and that was what you can make different kind of petrol and kind of benzene ring things from. That's a mixture of hydrogen and carbon monoxide. Copper, zinc and silver from their oxides, from their ores, they can be really good feedstocks, as well as sulfuric acid, which we can get from burning sulfur. Okay, so those are all feedstocks which we can use for different processes, so they will help you get to other products. Okay, so that's going to be important as well. And these are what consumer products are. And they are products that might be for the consumer, and we synthesize these, we make them from feedstocks. For example, paints, detergents, fertilizers, additives for your food, textiles, pesticides, cosmetics, solvents, plastics, acids, alkalis and medicine. They are all consumer products that we make in chemical industry. So we're going to have a look at a wee case study here for a chemical industry, and it's this plant that's called Lossychem. And it's fictional, it's made up, but obviously it's going to be a good idea for us to be able to practice these principles of process design, to be able to see how they all kind of attribute to how this chemical plant might run if it was to happen. So Lossychem brings ecological chemical plant to Moray. If you look here as well, just before we go here, this is called the Moray Firth up here, and this kind of whole area around here, which I'm going to draw about, this is called Moray. That's a region like Glasgow City Council, there'll be Moray Council, so all of that in there is called Moray. So Lossychem brings ecological chemical plant to Moray. Seawater can be electrolysed to produce 3 products. We can get sodium hydroxide, chlorine and hydrogen. Scientists and engineers at Lossychem have produced a pilot plant, and remember we said that's where you have looked at the research and then you're kind of scaling it up a wee bit more to see how it would work before you then go into your main plant that you make. This successfully splits seawater using electricity produced from renewable sources. The company and local planners must now decide whether to build a full-scale plant here, bringing much needed jobs to the local economy. So let's have a look at how these principles would apply to this plant. So let's have a look at the availability and sustainability of the feedstocks. Well, if you look at the map, you can see that Lossiemouth, which is where this place would be, because it's Lossychem, is right on the sea, which means that you would have a plentiful supply of seawater, the salty water, from that Moray Firth. And basically you've got unlimited supplies of that. So it's going to be dead easy to get because you just need to run a pipe from there and put some pumps in. And then also it's not going to run out, so it's definitely sustainable. In terms of the cost, it would have to be pumped into the plant, but basically the water itself is free. All we need to do is spend the money to get the pump and the pipes to put it into the plant. They also need to treat the water to make sure that none of the stuff that's in the water and any mud and stuff ends up in your final product. In case you want to treat it and filter it, and to make sure you're removing all the solids before you electrolyse it. Is there any opportunities for recycling? Well, you might get unreacted sodium chloride, but that can just be separated from the sodium hydroxide and fed back into the plant and used again. So you're recycling any unreacted sodium chloride solution, such as salty water. Energy requirements, all you would need is electricity to run the electrolysing. However, they have got this from hydroelectric sources, so you've got obviously lots of seawater, there might be wave power, or you could also maybe have some wind power up there as well. So if you're using renewable, that's probably going to keep the cost down, and also it's kind to the environment as well. Marketability of the byproducts, well, this one doesn't have any byproducts, so you don't have to worry about having to market that. You've got 3 marketable products, 3 products you can easily sell, so you don't have to worry about that. And the atom economy is 100% because all your chemicals that you're using, the sodium chloride solution, is turning it into the products, so you're okay with that. You don't have any atoms being lost to any byproducts, so it's 100%. So that is how this Lossychem would work, and those principles would apply there. Hopefully that makes sense. Okay, so what to do now is if you go to the worksheet, you'll be able to work through that and apply what you've learned here. Obviously, there's no calculations or anything, so it might be a wee bit boring, but just look at the definitions and look what we've looked at and try and apply them to the questions. I hope that makes sense.